Hello everyone. Today we will discuss the solution of gas dynamics and propulsion questions of GATE 2010 paper. In the year 2010, total 16 marks were contributed by gas dynamics and propulsion part, and we will discuss the solution of all those questions in this video. So the first question, isentropic efficiency eta D of a subsonic diffuser is defined as, four options are given. So this is 1 marks question. So for the solution of these questions, we'll first see the schematic of a subsonic diffuser. So this is a schematic of the subsonic diffuser, and this plane denotes the entry of the diffuser. This plane denotes the exit of the diffuser, so this diffuser basically sucks the air from atmosphere and it transfers the air to compressor, the subsequent parts of the engine. So if we so there will be a formation of stream tube in front of this diffuser when it sucks the air from atmosphere. So this is the stream tube, and this denotes the atmospheric condition from which the air is being sucked, right? So this is the schematic of a subsonic diffuser. Now if we have to draw the TS diagram, temperature entropy diagram, for this diffuser. So A denotes the ambient condition, 1 denotes the condition of the air at the entry of the diffuser, and 2 denotes the condition of the air at the exit of the diffuser. Now this air is being sucked from the atmosphere. So let's say the pressure of the atmosphere is PA. So this denotes the atmospheric condition at which the air is being sucked by this diffuser. Now PA is the static pressure, and the total pressure of the atmosphere would be denoted as POA, right? And this line, this straight line, denotes the isentropic condition. Okay. So if the flow inside the diffuser, subsonic diffuser, would have been isentropic, then there would be no loss in the diffuser. But in real case, because of friction, the loss will take place, and for that the total pressure would not remain constant in the diffuser. So at the exit plane, at this plane, the total pressure would be less than the total pressure at the inlet. That is attributed to the loss due to friction. So, and at this stream tube, which occurs in front of the diffuser, there will be some amount of compression will take place inside the stream tube. So so a little compression will take place. So this denotes the pressure at this surface, at this surface, the entry of the diffuser. Now, when the flow occurs in the subsonic diffuser, obviously some amount of compression will take place, and the static pressure will increase. So this denotes the static pressure at the exit plane of this diffuser. And this so this denotes basically denotes the process from 1 to 2, basically the compression from the entry of the diffuser to the exit of the diffuser, and this denotes the isentropic compression. Now P2 is basically the static pressure at the exit of the diffuser, and the total pressure at the exit of the diffuser is PO2, right? So total pressure at the exit of the diffuser is PO2, and since there is some loss taken place because of this wall friction, so PO2 would be less than POA. The process through the flow through the subsonic diffuser is basically adiabatic, so there is no heat addition or heat retraction is being taken place. So the total temperature throughout the process would remain constant. So TO1 would be equal to TO2. The total temperature would remain constant, and this point denotes the isentropic compression, right? So this is a TS diagram of this the flow in subsonic diffuser. Now the efficiency of this diffuser is defined as the isentropic change in enthalpy divided by the actual change in enthalpy across the diffuser. So the isentropic change in enthalpy across the diffuser is H. This HO2S divided by minus this HA, right? So that would be, and the actual process is HO2 minus HA. So this can be written as Cp minus TA divided by Cp TO2 minus TA. CP gets cancelled, so it becomes TO2S minus TA divided by TO2 minus TA, which is option A. Okay. Next question. For a multi-stage axial compressor with constant diameter hub, which of the following is true? The blade height decrease in the flow direction, blade height increase in the flow direction, blade height remains constant, and blade height first increases and then decreases in the flow direction. So if we draw a schematic of the of axial compressor, it would be something like this. So this is the hub. And these are the rotor blades fixed to the hub. Right, and then there is this casing. And there is stator blades attached to this casing between each rotor blades. So these are the stator blades between each rotor blade, and okay, stator blade, these are rotor blade. So as we can see in the schematic of this axial compressor, the area or the blade height basically decreases in the flow direction. So flow is taking place in this direction. So blade height decreases, and the reason of this is since at each and every stage of this axial compressor, the pressure increases. So pressure E increases at each stage of axial compressor. And since the pressure is increasing, so the velocity will decrease. But in axial compressor, it is important to keep the flow velocity constant. So for that, we need to make the area convergent so that this velocity can be kept constant. So since pressure is increasing at every stage, so velocity will decrease. But to keep the velocity constant, area is reduced so that the velocity throughout the compressor can be remain constant. So that is the reason. And so basically the answer is blade height decreases in the flow direction and the area is made convergent. So moving on to the next question. How does the specific thrust at constant turbine inlet temperature produced by a turbofan engine change with an increase in compressor pressure ratio? Increases, decreases, first increase and then decrease, first decrease and then increase. So basically, if we draw a plot of specific thrust with compressor pressure ratio for a turbofan engine, this is specific thrust, and pi c denotes the compressor pressure ratio. For a particular Mach number, the flow, the curve will be something like this. So which means first the specific thrust will first increase with compressor pressure ratio, then it reaches a maximum point, and then it starts decreasing for a particular Mach number. So this is the typical plot of specific thrust versus compressor pressure ratio for a particular Mach number. So the answer is first increases and then it decreases. Increases, then reaches a maximum and then starts decreasing. Next question. For a flow across an oblique shock, which of the following statement is true? Component of velocity normal to shock, it decreases while tangential component increases. Component velocity normal to shock increases while tangential is decreases, and so on. The four options are given basically. So if we see the condition, we basically draw the velocity components for both upstream and downstream of the oblique shock. So this is the compression corner, and if a supersonic flow encounters this compression corner, there will be a rise of oblique shock, right, in the corner. Now, so this is the incoming flow upstream of the shock, and this is the flow downstream of the shock. So of course the flow velocity will be constant to the surface. And now if we draw the velocity components normal and tangential to this oblique shock for both upstream and downstream, so the components will be something like this. This is the tangential component of incoming flow, and this is the normal component to oblique shock for the incoming flow. Similarly, for the downstream of shock, this is the tangential component. This is the normal component. Sorry. So this is the tangential component. Now we know from the properties of oblique shock that the tangential component of the velocity for both upstream and downstream of the shock remains constant. Right. So V1t would be equal to V2t. The tangential component, this is very important property for flow across an oblique shock. The tangential component of velocity remains constant. Now, if we see this normal component of the velocity, so this v1n is perpendicular to this normal shock, perpendicular to this oblique shock, basically. So for this component of the flow velocity, this basically acts as a normal shock, right? Because this velocity component is normal to this oblique shock. So and we know that across a normal shock, the flow velocity decreases. So, and since this v1n is normal to this oblique shock, so v2n must be less than v1n. So what we get is, for an flow across an oblique shock, the tangential component of the velocity remains constant and the normal component of the velocity decreases. So the answer is D. Component of velocity normal to the shock decreases while tangential component is unchanged. So this is unchanged. Okay. Next question. The stagnation pressure and the stagnation temperature inside the combustion chamber of a liquid rocket engine is 1.5 megapascal and 2500 Kelvin respectively. The burned gas have gamma is 1.2 and R 692.83. The rocket has a converging diverging nozzle with throat area this, and the flow at the exit of the nozzle is supersonic. So if the flow through nozzle is isentropic, what is the mass flow rate of the gases out of the nozzle? Okay, so if we draw a schematic of a convergent divergent nozzle, this is the chamber. So this P naught denotes the total pressure of the chamber, and T naught denotes the total temperature of the fluid at the combustion chamber. So this P naught T naught value have been given, and this is the throat, and this is exit of the nozzle. Now the value of the P naught is given as 1.5 megapascal, which is equal to 1.5 into 10 to the power 6 Pascal, and T naught is 2500 Kelvin. Gamma is given as 1.2. R is 6922 joule per kg Kelvin. And the rocket and the throat area of the nozzle is given as the throat area of the nozzle is given as this, and what we have to find out is that the mass flow rate through the nozzle. So there is a very important expression for mass flow rate through a variable area duct, and that expression is m dot equal to P naught A, sorry, P naught A root over gamma by under root R T naught m by 1 plus gamma minus 1 by 2 m square gamma plus 1 by 2 gamma minus 1. So this expression gives the mass flow rate m dot at a particular section of this nozzle where the area is A and Mach number is m. Okay, so this is the expression of mass flow rate of nozzle at a section where area, cross section area basically, where the cross-sectional area is A and Mach number is M. Now, since the flow inside this nozzle is isentropic and the flow at exit is supersonic, so since the flow at the exit is supersonic, the Mach number at the throat must be 1. So the Mach number at throat is 1. So basically the flow, the nozzle is choked, right? So and the mass flow rate through the, I mean, throughout the nozzle is constant. So if we find out the mass flow rate at the nozzle, that will be the mass flow rate at the exit, right? So if we by employing this expression, if we substitute the value of M as 1 at throat, and A is the area of the nozzle at throat, then you can find out the mass flow rate, right? So by substituting this value, by substituting the given values, what we get is M dot at throat is P naught. P naught is 1.5 into 10 to the power 6. Then throat area, which is 0.025, then under root gamma 1.2 by root over of R T naught. R is 692.83 multiplied by T naught, which is 2500, and M is 1, so this becomes 1 by gamma plus 1 by 2 to the power gamma plus 1 by 2 gamma minus 1, right? So since at throat the Mach number is 1, and this is the mass flow rate at throat of the nozzle. So we can compute this value, and it will come something 19.51 kg per second. And since the mass flow rate is constant throughout the nozzle, so throughout the nozzle, so mass flow rate at exit is same, which is 19.51 kg per second. So the correct answer is D. Next question. Consider a 1D adiabatic inviscid compressible flow of air with R 287 joule per kg Kelvin and CV 718 joule per kg Kelvin through a duct of constant cross-sectional area of, if the volumetric flow rate is this and the stagnation temperature is this, then the air temperature inside the duct. So we are basically asked to find out the static temperature inside the duct, and the stagnation temperature is given. So we know the empirical formula, the relation between the stagnation temperature and the static temperature. So static temperature we have to find out. So if we write the relation between the stagnation temperature and the static temperature, it is m square, right? 1 plus gamma minus 1 by 2 m square. So this gives the ratio of stagnation temperature to static temperature, where m denotes the Mach number. Now this gamma value is given, so we have to find out the Mach number m, right, to get T. So m is basically velocity of the fluid by velocity of sound. Now Q is the volume flow rate, which is 680, right? So this is basically area into velocity. Now area is given as 1 meter per second square. So if we substitute that, we get V as so if we substitute the value of area as 1, then we get V as V will be 680 meter per second. So we have to find out A. Now A is basically root over of gamma RT, right? And gamma value we have to find out. So this CV is given. CV is given as 718 joule per kg Kelvin, and this can be written as CV can be written as R by gamma minus 1, right? So, and since a value of R is given, so from this we can find out gamma. So this is basically equal to 7918. So from this we can find out the value of gamma. It will come something around 1.4, right? So basically m is, from this we get m is 680 divided by root over of 1.4 into R is 287 into T, and the value of this T we have to find out. So if we find out this expression of m in this equation, what will we get? Get T naught by T equal to 1 plus gamma is 1.4 minus 1 by 2 into m square, and m is nothing but 680 divided by root over of 1.4 into 287 into T. So it's square. Now if we, and the value of T naught is also given. The value of T naught is given as 580. So we substitute this 580.05 divided by T equal to 1 plus, this will come as 0.2, and 680 square by 1.4 into 287 into T. Now if we just solve this equation, we'll find the value of T as 350 Kelvin. So this is the answer. So the air temperature inside the duct is 350 Kelvin, option B. Next question. A two-stage chemical rocket having a same specific impulse of 300 seconds for both the stages is designed in such a way that the payload ratio and the structural ratio are same for both the stages. The second stage of the rocket has the following mass distribution: propellant mass, structural mass, and payload mass, and GE. So G value is given, and sorry, because this question has not come completely. So the question was, we had to find out the final velocity. So we had to find out the, I'll just write the question here. Find out the final velocity obtained by the payload. Okay, so we have to find out the final velocity obtained by the payload of the of a two-stage rocket. So if we draw a schematic of a two-stage rocket, it will be something like this. This is a structural mass denoted by Me1. This is propellant mass denoted by MP1. Again, the structural mass and the propellant mass, and this is the payload mass in PL. Now this denotes the second stage of the rocket, and MO2 is the total mass of the second stage of the rocket, and this of course the total mass of the rocket before the rocket starts, before the rocket gets start, right? So MO1, that is basically MO, so that is the total mass of the rocket. Now we have to find out, so what we are given is the propellant mass of second stage, that is MP2, is 10208 kg. Structural mass, that is Me2, is 1134 kg. Then payload mass MPL is 700 kg, right? And GE is nothing but 9.8 meter per second square. Okay, and the specific impulse is also given 300 second. So we have to find out the final velocity obtained by the payload, and the final velocity obtained by the payload is nothing but the velocity is basically the burnout velocity at the end of the second stage, right? So the final velocity obtained by the payload is the burnout velocity at second stage, right? So if we just write the expression of this burnout velocity at second stage, it is G ISP log of, so this is the where n is the mass ratio of the rocket. So this is the expression of burnout velocity at second stage for a two-stage rocket. Okay, so the mass ratio n can be written as 1 plus lambda by epsilon plus lambda, where lambda is the payload ratio, which is given as MPL, the mass of payload, the payload mass divided by propellant mass plus structural mass, and epsilon is structural ratio, is ME, is denoted as the ratio of structural mass divided by propellant mass plus structural mass, right? So, and since it's, the payload ratio and the structural ratio for both the stages are same, so lambda 1 denotes the payload ratio of stage 1, and lambda 2 denotes the payload ratio of stage 2, and they are equal, so they're denoted by lambda. Similarly, epsilon 1, that is structural ratio of stage 1, is equal to structural ratio of stage 2 and denoted by epsilon. Now MPL, MP, and ME, these values are given in the question. So if we just substitute those values, we'll get lambda as 1700, that is the payload mass, divided by 10208, the propellant mass, plus structural mass 1134. So it will come something around 0.1498, and epsilon will come as the structural mass, that is 1134, divided by the propellant mass 10208 plus structural mass, right? So it will come something 0998. Now by substituting this value of lambda and epsilon in the expression of n, that is the mass ratio of the rocket, so we'll get the value of n now. If we substitute this value of n in this main expression, we'll get V burnout at second stage is 9.8 multiplied by ISP is 300, and ln of this one plus 0.1498 by 498, this square, so this meter per second. So it will, if we just do this calculation, it will come something around 9879 meter per second. So this is the answer. So this is the velocity of this is the final velocity obtained by the payload, right? So velocity obtained by the payload, right? So that's the answer. Next question. A missile with Ramjet engine is flying in air, and the temperature at the inlet and outlet of the combustor is given. The heating value of the fuel is this, and the burner efficiency is 90%. So considering the fluid to be air, the fuel to air ratio of this engine we have to find out. So basically you have to find out F is how much. Now if we draw a schematic of this combustion chamber, if we draw a schematic of the combustion chamber, constant area, and this denotes the entry of the combustion chamber, and this 2 denotes the exit of the combustion chamber, and heat is being added in terms of injected fuel, right? So this is Q is the heat added, which is nothing but mf dot cv. Mf dot is the fuel flow rate, and cv is the calorific value of the heating value of the fuel. So, and now if we so this is the entry of the combustion chamber. Let's say the mass flow rate of the air entering the combustion chamber is ma dot. So the total mass flow rate coming out of the combustion chamber will be ma dot, the mass flow rate of air which entered inside the combustion chamber, and the mass flow rate of the fuel which was injected inside the combustion chamber, right? Now if we just apply the energy balance equation in this combustion chamber, so the total energy of the flow of the fluid entering the combustion chamber is nothing but, so applying energy balance equation in the combustion chamber, the total energy of the fluid entering the combustion chamber is ma dot cp to1, right, plus the, okay, 1 second. So total energy of the fluid entering the combustion chamber plus the energy released from injected fuel is equal to the total energy of the fluid at exit of combustion chamber. Now total energy of the fluid entering the combustion chamber is nothing but ma dot cp to1, and the energy released from the injected fuel is nothing but this burner efficiency is given as 90%, which is eta b into mf dot cv. Now this eta b burner efficiency is defined as the enthalpy released by total available enthalpy. Now this is the total enthalpy of the fuel which was injected, but the entire enthalpy will not be available for the combustion process. So the combustion process, the enthalpy released from this injected fuel would be eta b into the available enthalpy, right? Total available enthalpy. So this is the energy released from the injected fuel, and this will be equal to the total enthalpy of the fluid at exit of the combustion chamber. Now we have to find out F, which is F is equal to mf dot by ma dot. So if we just take common ma dot, take common from both sides, it will become cp to1 plus eta b into mf dot by f. Oh, sorry. mf dot by ma dot cv equal to 1 plus mf dot by ma dot into cp into to2, right? Now this value of cp is given, the value of to1, that is the total temperature of the fluid at entry of the combustor, is given, and to2, that is the total temperature of the fluid at exit of the combustor, also given. So if we just substitute this value, what will we get is so if we just just substitute the value. What will we get is Cp into TO1. TO1 is 1200 plus F into eta B, which is 90%, so 0.9 into Cv, which is 43 megajoule. So this is 10 to the power 6 joule. So this would be equal to 1 plus F into Cp, which is 1005 multiplied by TO2, which is 2500. So if we just solve this equation, we'll get F as 0.0361. So this is the ratio of fuel flow rate to mass flow rate inside the combustion chamber. So this is the correct answer. Moving on to the next question. The inlet stagnation temperature of a single stage axial compressor is 300 Kelvin and the stage efficiency is 0.8. The following conditions exist at the mean radius of the rotor blade, that is blade speed is 200, axial flow velocity is given, inlet and outlet blade angles are given, and Cp gamma value are given. So what is the stagnation pressure ratio for the compressor? So if we just draw the velocity triangle for this flow at the single stage axial compressor, it will be something like this. Though drawing the velocity triangle is not required for this particular problem, but still for understanding, if we draw the velocity triangles, it will be something like this. This is at entry of the blade. This is exit of the blade. Now this is CA1, axial velocity CA2. And this is the blade velocity U, the value of which is given. And this angle is inlet blade angle beta 1. And this angle is beta 2, outlet blade angle. And this CA1 is basically equal to CA2. The axial velocity remains constant. Now if we draw the TS diagram of the flow across our compressor, so this line denotes the entry of the compressor, this line denotes the exit of the compressor, and at this point, it is the entry point. And this straight line denotes the isentropic process. So this is the total, this is the condition at the exit of the compressor, and this denotes the isentropic condition at the exit of the compressor. So the compressor efficiency will be denoted as the ratio of the isentropic work done divided by actual work done. Divided by actual work done. So this would be minus H1 divided by HO2 minus HO1. So this can approximately be written as TO2S minus TO1 divided by TO2 minus TO1, right? And this value of eta C is given as 0.8. So this value is given as 0.8. Now the total work done by the compressor, the total work done by the compressor per unit mass flow rate is Cp TO2 minus TO1, right? And all this total work done by the compressor can also be written in terms of this blade velocity and axial velocity and the flow angles. So U is given as 200 meter per second and CA is given as 160 meter per second, and beta 1 is 44 degree, beta 2 is 14 degree. So the total work done by the compressor per unit mass flow rate can also be written as this U, the blade velocity, CA, the axial velocity, into tan of beta 1 minus tan of beta 2. And since both the expression gives the same quantity, that is the work done by the compressor per unit mass flow rate, so these two will be equal. Right, now we know the value of Cp, we know the value of U, CA, beta 1, beta 2. We can just substitute those values and we'll get this TO2 minus TO1, that is so from this we get TO2 minus TO1 as 22.809 Kelvin. Now if we substitute this in the expression of eta C, so we'll get 0.8 equal to TO2s minus TO1 by 22.809. Now if we take one common, minus 1 divided by 22.809. Now this TO2s by TO1, that can be written as the pressure that can be written as in terms of this stagnation pressure across the compressor. So this comes from the isentropic relation of gas. So right, substituting this in this expression, it will come, TO1 is given as 300 Kelvin. So 300 1 to gamma minus 1, gamma is 1.4, so basically it comes this divided by 22.809. Now if we just substitute, if we just calculate this, solve this equation, we'll get the stagnation pressure ratio across the compressor, PRS, which is PO2s by PO1. So this will come something around 1.23. So this is the answer, the stagnation pressure ratio across the compressor. This is the correct answer, 1.23. So these were all the questions from gas dynamics and propulsion in the year GATE 2010. Thank you.